Okay, thank you for the introduction. So I'm Hamza. I'm from the Hebrew University. I'm a PhD student at Ronen Rappaport's lab. And today I'll be talking to you about room temperature sources. So thanks to the very good first two talks in this session, I don't have to do much introduction. So I'll just go right into the topic. So our goal is to actually try to improve the characteristics of room temperature sources, single photon sources. And we're at the Single Photon Workshop, so we don't have to actually say why we want to do this. But the room temperature sources that we really usually deal with are, for example, colloidal semiconductor nanocrystal quantum dots, and different types of defects in nanodiamonds or in bulk diamond even. So what we actually do in the group is we try to improve the brightness and purity of these sources, and I'll be talking a bit more about this. So the first part of the talk, I'll talk more about how we deal with the brightness of these sources. So we all know that we need a very high rate source for quantum applications, and the question is, how can we do that? And well, usually we focus on one or two of these two aspects. So we have this brightness that depends on the decay rate of the emitter and on the collection efficiency of your source. So you can increase the collection efficiency by coupling your emitter into different types of antennas to get better collection into your NA, or place it into a cavity to increase the Purcell factor. So typically people have used different types of resonators. For example, these are dielectric resonators with typically cryogenic sources, such as micropillar cavities or photonic crystal cavities, which offer very high directionality and high Purcell factor with high purity and indistinguishability, but they operate at cryogenic temperatures. And for room temperature sources, they're not ideal because they have a narrow bandwidth, and sort of most of the emission is lost by the recoupling. And just a small thing is you have to tune the resonance of the cavity and the emitter to get into the same mode. Another option, which is really famous for room temperature sources, is plasmonic resonators. So you can use, for example, patch antennas or phased array antennas, such as the Yagi-Uda antennas, but which offer really high broadband operation. But you have to actually choose either high directionality or high Purcell factor for a typical structure. And they require precise positioning of the emitter due to the low mode volume of these types of resonators. So what we do in our group is we sort of combine the two approaches. So we have this sort of hybrid dielectric bullseye antenna, where the emitter is placed inside this dielectric slab waveguide, and which is surrounded by a circular Bragg antenna. So basically how this operates is that you excite your emitter emits preferentially into the waveguide mode and then gets diffracted by these circular rings, and we tune these rings in such a way that you have constructive interference into a very low angle. And we've been able to show consistently collection efficiencies of the order of 80% into an NA of 0.5, which means that you can go towards directly coupling fibers to these types of sources without any additional optics on the way. So first we did this basically with colloidal nanocrystal quantum dots, and what you see here is a fluorescence map where we deterministically position the single QD in the center of this bullseye. The red line is the outline of the antenna. And we measured the collection efficiency and compared it to simulation. We see very high collection efficiencies. I'll get back to this in a minute. And by doing some time-gated filtering, we get very nice G2 measurements. Now, this video here will show you the back focal plane as a function of wavelength. So these emitters at room temperature, they have this broadband emission over 40 nanometers. So our goal is that this antenna will operate over this very broadband range. And what you'll see here is this back focal plane image over the whole spectrum of this quantum dot. And what you see is as the emitter's wavelength comes into resonance with the antenna, you get very high directionality at the zero angle here. But over the whole spectrum of the antenna, the emission is mostly within 10 degrees from the normal We also did the similar thing with nanodiamonds containing NV centers. Again, this is a G2 measurement of that, and this is a polar intensity plot showing this very high directionality that we see again with very high collection efficiency. So the natural question is, okay, this is good collection efficiency, but how does it compare to other schemes? So again, we just plot these two collection efficiency curves for the nanodiamonds and for the colloidal quantum dots and compare it to other sources. For example, here you have micropillar cavities, tapered nanowires, and a photonic crystal cavity here. And you can see that our antennas operate quite well compared to these schemes. However, these antennas don't have any Purcell factor, and so basically it just does some directionality. And what we want to do is actually introduce a plasmonic resonator at the center that will give us a large Purcell factor here. So this is a nanocone plasmonic resonator, which has been shown previously to have high Purcell factors. So the idea is to just combine both of these. So put a nanocone at the center of your bullseye antenna, and then you can get simultaneously high collection efficiencies with high Purcell factors. And actually we did some FTDD simulations on this, and we show that we can get into the NA again something on the order of 80% with a Purcell factor of several hundred, which gives us a brightness enhancement of about 1,000 compared to what you would get from the same emitter in free space. Okay? And we've made these antennas, and now we're actually at the stage of coupling the emitters to the tips of these nanocones. So this is the first part of the talk where I focus mostly on the brightness of the source. Now I'll talk a bit more about the purification of these sources. So again, we have this problem of purity with these room temperature sources. So typically they're not so pure, especially quantum dots. As many of you know, they have significant multi-exciton emission, and at cryogenic temperatures, it's relatively easy. You can spectrally resolve these lines, and you can spectrally filter them out. At room temperature, homogeneous broadening doesn't offer you this option. So, for example, for these colloidal quantum dots, we like them because they're easy to fabricate. They operate at room temperature. You can tune their spectrum. They're easy to integrate. But in recent years, when people have tried to increase the stability of these sources, so they were blinking and all that, and when they increased the stability, the bi-exciton quantum yield increased, which led to a lower single photon purity. And of course, filtering doesn't work spectrally, or polarization-based filtering doesn't work. So we are left with this temporal domain, so temporal filtering techniques. So these rely on one of two factors, either that the bi-exciton-exciton emission is cascaded, or that the bi-exciton lifetime is shorter than the exciton lifetime. And this is shown here in this diagram. So when you start with the ground state, you excite to the bi-exciton state, for example. Then you're left with two excitons in your quantum dot. And since there's 4 different recombination paths, it has a lifetime that's 4 times shorter than the exciton lifetime. And then one of these excitons recombines, yielding the exciton state with a bi-exciton quantum yield that will give you a photon. And then again, it will recombine, giving you another photon. So this is, with these probabilities, you'll get 2 photons from this source. So this is actually a problem that's been exacerbated again by increasing the photostability of the sources. So the question naturally arises is, how can we sort of distill these single photons out of these 2 photon events? So the easiest and most natural way is just to apply a time gate filter. Okay, so you have this filter, your bi-exciton lifetime is shorter than the exciton lifetime. Apply this filter, throw out whatever comes before this filter. Okay, so this is relatively simple, but if you plug in the numbers, you find that there's a significant trade-off between purity and efficiency, especially if the bi-exciton and exciton quantum yields are high. So in this case, if you want higher and higher purity, you'll have to give up more and more efficiency. So specifically for the cases where the bi-exciton and exciton quantum yields are high, you need different kind of methods to get rid of this bi-exciton emission. So one of the methods we developed is, okay, instead of throwing out the photons that come before, use them in sort of a heralded kind of scheme. So apply a time gate here. Whatever comes before this time gate, you send to an idler port. Whatever comes after, you send to a signal port. And then in a post-processing step, you only choose these 2 photon events. This is a passive scheme, of course, and so this time gate is fixed. You choose it at the beginning of your experiment, and then it's fixed. And it can, by definition, if you start out with a 2 photon event, then your purity is by definition 1. And the efficiency goes up to 63%, 67%, depending on exactly what the quantum yields are. Another method we developed is actually active switching. So instead of just fixing what your time gate is, take these 2 photons. When the first photon is detected, switch to the signal port, and then you'll get 1 photon in the signal port, basically. It's very simple, conceptually. The issue here, of course, is if there's a finite response time between the actual detection event and the switching of the source. So if you calculate this, it depends on the detector switching time and the switch rise time and everything else. Then this is called the response time of the system. And if, of course, the 2 photons are separated by less than this, they'll both be lost. They'll both go to the idler port, and the signal photon will be lost. So in realistic situations, we found that the response time is roughly on the order of 5% of the exciton lifetime. So this can offer actually high purity without any loss of efficiency. Again, if you have 2 photon events, the purity is by definition 1 in this case, and so you don't have to worry about that. And the efficiency can asymptotically reach 1 also. So in order to compare this, in order to make a fair comparison, we drew some sort of phase diagram where you have here the exciton quantum yield and the bi-exciton quantum yield. And what you see here is when you're below this line, basically the time-gated filtering is better. When you're above this line, the heralded methods are better. And what you see actually is these are examples of nanocrystal quantum dots with different quantum yields, and you see that we're already in the region where the heralded methods are actually relevant in this case. So, yeah. So we wanted to do some experimental work on this, but we didn't want to do actually the physical implementation yet. So what we did is, basically what you have here is, again, this confocal microscope. You get your emission, and here you're supposed to have your switch that actually switches between the 2 ports. So instead of doing that, what we did is we put a 50-50 beam splitter, and afterwards we put this regular Hanbury-Brown twist experiment, and on the time tag events, we emulated the response of a switch. How would a switch act like? And we saw that before we could obtain a purity we started out with a quantum dot that had a purity of less than 90%. And using these methods, with emulating the switch, we got purities of 99.5%. So it really increased the purity of the source. So these are very high purities comparable to state-of-the-art systems. And of course, then we can emulate different response times and see how the experimental values agree well with the theoretical expected values. So I guess I was fast. So at the end, I'd like to thank the people that made this possible. With the colloidal quantum dot work, it was done with collaboration with Jennifer Hollingsworth at Los Alamos. Nanodiamond work was done with Oliver Benson's group, specifically Nico Nicolai. And of course, my partner on the project, Boaz, and my supervisor, Ronen Rappaport. So to summarize, I've shown you methods that are methods to manipulate the rate, directionality, and purity of our single photon room temperature quantum emitters, which can give us high collection efficiencies and high Purcell factors, in addition to high purities. So the goal now is actually to couple these quantum dots to these nanocones and do an actual physical realization of these switching techniques, and eventually to build a plug-and-play source where you electrically excite the quantum dot and collect it directly into a fiber. And thank you very much.
Thank you for this nice talk. There's room for questions.
So So thank you for the talk. So I would have a couple of questions. The first one is whether you have also some results about the total emitted power. Because, I mean, I don't understand this collection efficiency to what is normalized. Because you're very close to a silver layer, as far as I understand.
It's a gold, but it's not very close. It's 100.
So anyhow, I mean, I know the problems, and I know that often they do not grow exactly the same way.
Yeah, I understand. Yeah, there are. Okay, plasmonic losses are nearly zero in this case. The emitter is not that close to the metal to introduce any plasmonic losses. The emitters we choose have long lifetime, so the lifetime is between 60 and 90 nanoseconds. So the rates are pretty low compared to what you showed. But the quantum yield, we didn't see any deterioration of the quantum yield by placing inside the quantum.
But this normalization is calculated, so this efficiency is calculated with respect to the same emitter in bulk?
Yes.
Or, okay.
Yeah. So you know the rate, what the quantum yield should be, and you check them out, and then when you put it inside the antenna, you know what you're supposed to get and how much you actually get. So you normalize that, yeah.
And one last question quickly. So the spectral bandwidth, you want broadband redirection. So if you say, so what is the bandwidth for which you get these 80% efficiency?
Well, it depends on what the NA is, right? I hope I have
0.5 you said, right?
Yeah, so I hope I have some slides on that. But yeah, so we saw that for 0.5 NA, it's about 100 nanometers. You can get this 80%. So.
Okay, there's one more question over there.
Can I ask about the, so in the final implementation with the nanocone, you expect a very good per cell enhancement, so you're going to speed up the rate of emission of the quantum dot.
Yeah.
But are you also going to speed up the rate of the Biaxton decay, and therefore how fast will your switch have to be, and what kind of switch could you use?
Yeah, so actually what we took into consideration when I said this 5% is actually this final implementation. So the lifetime we expect will be around 2 nanoseconds, and then we did these calculations on, for example, using an SN-SPD detector with fast enough switch. The problem is that now in the visible where we are, there's not enough fast enough switches, but if we move to the IR, then there's nice enough. And there are emitters in the IR currently, so.
And the switch will, I guess, end up having some kind of 3 dB or more loss, and so you factor that into your final efficiency.
Of course, yeah. And yeah, it's a good point. Here, when you plot this phase diagram I showed you, basically your loss is also, you can take your loss into the quantum yield. So you can plot this as the loss times the quantum yield, the loss times the quantum yield here, and then figure out whether or not which scheme is better for you to work with.
I see. Thanks. Yeah.
All right. If there are no more questions, let's thank the speaker
yes.
again.